So welcome you back to this module. So what we were doing last time was that we were discussing the properties of the maximum likelihood estimators. We saw that maximum likelihood estimators in many situations is a root of the likelihood equation, which basically is obtained by differentiating the likelihood equation and finding the critical point. So that means one is or one may be interested in knowing what is the nature of roots of the likelihood equation. And then in that context we did a result last time which says that there would always exist a sequence theta and hat star x of estimators such that probability that theta and hat x is a root of the likelihood equation L x prime theta is equal to 0. This probability would always go to 1 as n goes to infinity. Not only that, the same sequence theta and star would also be local maxima. That probability would also go to 1 as n goes to infinity. And such a sequence would always be consistent. So that is the result which we saw last time. As a consequence of this result, you could say that if your likelihood equation has a unique root, then such a sequence would always be consistent. Not only that, if it has a unique root and it corresponds to the local maxima, then it would also be consistent. And then you can say that there is a consistent, unique consistent estimator, which is a unique maximum likelihood estimator which is consistent. Now what we are going to do today is we are trying to talk about the asymptotic normality of the maximum likelihood estimator under certain conditions. So what we are going to talk about is the asymptotic normality of any consistent sequence of roots of the equation L x prime theta is equal to 0. So let me do this result. Suppose A1 to A3 hold. What were the A1 to A3 hold? Basically that theta is an open set of real line. Your support does not depend on theta. And what was the so these are the two main conditions. So suppose A1 to A3 hold. Further, I assume the following conditions. So let me recall what was the third condition over here. So the third condition which we assumed was that the model is identifiable. That means two different thetas would give rise to two different probability distributions under consideration. So there is no identifiability issue. And theta is an open interval and the support does not depend on theta. So suppose these conditions hold. Further, assume that for every x in the sample space chi star, which I am taking as collection of all those x, such that f theta x is positive. F theta x is thrice differentiable actually, with respect to theta. And the third derivative is continuous. Theta belonging to capital theta. So for every x for which the density is positive, f theta x is thrice differentiable with respect to theta, and the third derivative is continuous in theta belonging to theta. So let me write down this as P. Second thing is, if it is thrice differentiable, I'll assume that I can differentiate it thrice under the integral sign. So what I assume is integral over del by del theta cube f theta x d mu is same as d cube by d theta cube integral over f theta x d mu. Of course then this has to be 0 because integral over f theta x d mu is 1. So if you differentiate it thrice, you get this as 0 for every theta belonging to theta. So similar kind of regularity conditions we required when we were talking about Cramer-Rao lower bound, except that here I want my f theta to be thrice differentiable. Second thing is my information on a single observation, which can be written as expected value of del by del theta log f theta x1 whole square. So these are information contained in a single observation. This is always positive and finite. This is always between 0 to infinity for every theta belonging to theta. Second thing is my third derivative is bounded in a neighborhood of any theta. So for every theta star belonging to theta, there exists a c greater than 0 and a function whereas c and mx depend on what theta star is, says that the third derivative so let me write down small x is always less than or equal to m of x for every x belonging to x star and theta belonging to theta star minus c to theta star plus c. So that means the third derivative with respect to theta of log f theta x is bounded by mx, and mx is integrable. Now such conditions are normally satisfied in the exponential families. So exponential families, you can blindly use this result. So if in such a situation let theta n hat star x be a sequence of consistent roots of the likelihood equation, be any consistent sequence of roots of theta is equal to 0, then you will have asymptotic normality. Then root n theta n hat star minus theta. So if theta naught is the true value, goes in distribution to normal 0, 1 upon I theta naught. So note that this was the smallest Cramer-Rao lower bound in the limiting sense. So in that sense, such an estimator would be asymptotically efficient. Now one consequence which you can draw from here is if your likelihood equation has a unique root, then you know that such a root would be consistent. So this result says it will not only be consistent, it would be consistent and asymptotically normal, provided this equation has a unique root. Because by the last result we know that if it has a unique root, then such a root would be consistent. And in fact, if you could further verify that it is a local maxima, then it would be in fact maximum likelihood estimator. So in certain situations, this result may talk about the consistent and asymptotic normality of the maximum likelihood estimator. So proof is simple. The usual technique is apply the Taylor series expansion. So what I do is I give the hint outline of the proof. So Lx prime theta n hat star. So I expand everything around theta naught. So this becomes Lx prime theta naught plus theta n hat x minus theta naught Lx double prime plus theta n hat x minus theta naught whole square by factorial 2, which I can write down as 2 Lx. Let me write down the third derivative as Lx3 let me write down over here as theta n hat double star, where theta n hat star lies between theta n hat x and theta naught. Lies between. You have put this as theta n star, so I'm expanding this. Because theta n hat star x is the root of the equation Lx prime theta is equal to 0, where theta n hat double star x lies between theta n hat star x and theta naught. Now note that this goes in probability to theta naught, and this quantity is in between. So in fact, this would imply that theta n hat star x will always goes in probability to theta naught. In fact, it would be going almost surely to theta naught, one can prove. One can prove it using rigorous argument. Going in probability is obvious because theta n hat double star x lies between this, and this goes in probability to theta naught, and you know that convergence in probability, for convergence in probability, Sandwich theorem is applicable. Okay, so if I do that, this I take theta n hat star x minus theta naught as common, then it becomes minus theta n hat star x minus theta naught. This I am taking common. Then it becomes Lx double prime theta naught plus theta n hat star x minus theta naught divided by 2 Lx 3 theta n hat double star, right? This becomes minus Lx prime theta naught. So this gives you root n theta n hat star x minus theta naught is nothing but minus root n theta naught divided by all this, which is nothing but Lx double prime plus theta n hat minus theta naught by 2 Lx 3 hat double star. What I can do is I can divide numerator and denominator by n, so it becomes minus 1 by root n Lx theta naught divided by 1 upon n Lx plus theta n hat, this will be theta n hat star minus theta naught by 2 Lx triple prime. It's not a very rigorous argument, but I'm trying to make it as rigorous as possible. Let us try to see where does this goes to. Does it go to something in distribution? This looks like would go in probability to something. This looks like, because it is bounded, theta n hat star minus theta naught goes in probability to 0. So this looks like this will go in probability to 0. So let's try to see one by one. So what do you get? This should be Lx prime theta naught, right? Everywhere, because this is what comes over here. So let us look at 1 upon root n Lx prime theta naught. It is a log likelihood. So log of summation I is equal to 1 to n f theta xi. So this becomes 1 by root n del by del theta naught summation I is equal to 1 to n log of f theta naught xi, which is same as 1 by root n summation I is equal to 1 to n f theta naught prime xi by f theta naught xi, which is same as root n I take outside, then 1 by n summation I is equal to 1 to n f theta naught Note that expected value of this quantity is 0, right? Expected value of this quantity, because integral over f theta naught x dx is 0. Sorry, integral over f theta naught x d mu is 1. So I differentiate it, I get integral over f theta naught prime x d mu is 0, which is same as integral over f theta naught prime x divided by f theta naught x into f theta naught x d mu is 1. So which is same as expected value of this is 0. So I can write down this as 0. So what do you get? These are IID. So it is a sample mean of IID minus the mean of the individual, because expected value of this is 0. Root n. So by central limit theorem, this goes in distribution to normal with mean 0. And the variance of the single observation over here, so variance theta naught of f theta naught prime xi by f theta naught xi. But this is nothing but how much? Variance of del by del theta log of f theta naught x1. You can write down this as x1 because all our xi's are IID, which is nothing but I theta. So this is same as normal 0 I theta naught, right? Because it's a variance of partial derivative of log of f theta x. Variance of partial derivative of log of f theta x is nothing but I theta. So this goes in distribution to normal I 0 theta. So what I know is this numerator goes in distribution to something. So if I can show that denominator goes in probability to something, by Stutsky's lemma I have proved the asymptotic normality. So let us try to see what happens. So let us consider now the first thing in the denominator, which is 1 upon n Lx double prime theta naught, which is same as 1 upon n del by del theta which is same as 1 upon. Now, in fact, if you recall, this is again sequence of IID. Its expected value we have assumed is finite, and its expected value is same as minus of I theta naught. So this goes, in fact, almost surely to I theta naught by strong law of large numbers, because, sorry, minus I theta naught, because I theta naught is the expected value of this quantity. So this quantity goes in probability, or almost surely, in fact, to I theta naught. Now I need to consider theta n hat star minus theta naught by 2. Now theta n hat star minus theta naught goes in probability to 0. So I just need to see what is the behavior of this quantity. Everywhere I have divided by n. Right? So this would be n over here. So I need to consider what is Lx3n. So let us consider theta n double star, which is nothing but 1 by n Lx3 is basically del cube by del theta cube, summation I is equal to 1 to n, f theta log of f theta xi. Actually, if you look at, if I had assumed that expected value of this is finite, it could have gone again by strong laws of numbers to something. It would have gone something by strong law of large numbers to something. This would have gone to 0, and everything would have gone to 0, and things would have been done fine. So just assuming that expected value of del cube by del theta cube log of theta xi is finite is fine. But what I have assumed is this is bounded by something which is finite. So this would, this is same as that theta is equal to theta n hat star. I know that third derivative is always bounded by mxi, so this would always be less than or equal to 1 by n. Summation I is equal to 1 to n mxi. And I know that this goes in probability to expected value of m of x1, again by the strong law of large numbers or weak law of large numbers. So what I know, in certain sense, theta n hat star minus theta naught is going to 0 in probability. This is bounded in probability. So this everything together would go in probability to 0. This was going to minus I theta naught. So everything together, if you combine it, I get this result by Slutsky's lemma. Right? So combine this as 2, this has 1, and this has 3. So 3 basically gets from the fact that this implies that theta n hat star minus theta naught by 2n Lx 3 theta n hat double star goes in probability to 0. Because this goes in probability to 0, this we have shown is bounded almost surely, so this will go in probability to 0. So now combine 1, 2, 3. This goes in distribution to something, this goes in probability to something. So by Slutsky's lemma, everything will go in probability to normal 0 I theta naught upon I theta naught, which is same as root n theta n hat star minus theta naught goes in distribution to normal 0 1 by I theta naught. So this is a very nice result in the sense that under these conditions, if your likelihood equation has a unique root, Lx prime theta has a unique root which is theta n hat star x, then you know that it is consistent by the result done before. Not only that, it would be asymptotically normal, so it would be can. It is a MLE or not, that I do not know, but I can also say that it is MLE provided Lx prime theta is equal to 0 has a unique root, which is also a local maximum. Then theta n star x would be the unique MLE, and it would be can by this result. So everything boils down to the fact that under what conditions I have a unique root of the likelihood equation. Before that, let me do a small corollary to this result which we were saying, which in fact I have just stated, but let me write down in words. So the corollary is as follows. Under the assumptions of last theorem, suppose that Lx prime theta is equal to 0 has unique root So let me write down this, has unique root for every x and theta. Sorry, for every x and n. Then the MLE, provided it exists, then it will be a root of this equation, is can and asymptotically efficient. Can is just follows from the last theorem, asymptotically efficient because it attains the Cramer-Roll over bound 1 upon I theta naught. So very powerful result in certain situations. So the only thing now you need to satisfy is the situations where MLE is unique solution of the Lx prime theta is equal to 0. What one can see is in the exponential family, this condition is always satisfied. So let me write down this one parameter exponential family. Now proof you can see in the Lehmann's book. I am not going to do it. You might have done it in the last course. Let my density f theta x or probability mass function is e to power theta tx minus psi theta hx. So that this is the case, for example, for most of the distributions which consider geometric, negative binomial, normal, gamma, chi-square, and so on, with respect to sigma finite measure mu. So for example, for discrete case, this mu would be a counting measure. For continuous case, mu would be a Lebesgue measure, where theta is the natural parameter space. So that means theta belongs to capital theta, which is collection of all those eta such that this quantity is finite. Collection of all those eta belonging to R such that integral over eta tx minus psi eta d mu. So this is anyway can go away, e to power eta tx hx d mu is finite. Then exponential families are very nice families because they satisfy all the regularity conditions which are required for deriving the Cramer-Roll over bound, or the one which are required for studying the MLE properties of the MLE. Then it can be shown that assumptions of last theorem are satisfied. So basically what it is, this would be differentiable. Exponential differentiability is not a problem. Only condition which you need is size would be differentiable and so on. If psi theta is differentiable, moreover, for every theta belonging to theta naught, of course this theta naught is the interior of theta. So here I'll consider my theta to be interior. If this is not an open set, I'll consider the interior of the parameter space so that my last result is applicable because that requires theta to be open. So either theta should be open. If theta is not open, I'll restrict my parameter space to only interior of theta. So for every theta, all moments of Tx1 exist, And it can be shown that this psi theta is infinitely times differentiable. At any theta belonging to theta naught. Not only that, if I consider expected value of Tx, that turns out to be psi prime theta. Variance of Tx turns out to be psi double prime theta. See, I theta is always less than infinity. Not only that, I theta is same as psi double prime theta, which is same as variance of T of x phi. Now, proving this result is straightforward using the result which is given in Lemon. So, what we saw is, at least in the exponential family, things are simpler. Now, the only thing is, I have to see whether in exponential family, if I is of this type, and I have to estimate theta, can I say that the likelihood equation Lx prime theta is equal to 0 has a unique root? Then I can conclude a lot of things. Not only that, if I can also claim that that unique root which I get is also the MLE, then I can talk about consistency and asymptotic normality of maximum likelihood estimator in the exponential case. So that we'll do in the next module. So thank you very much. See you in the next module.